Good afternoon. We resume our speech on materials from where we stopped last time. Basically, last time we were talking about steel, and we were saying that steel is the material closest to the ideal one, which of course it's a model. And also that steel can have different phases, different ways it is arranged as a microstructure. This is important because ultimately it allows the possible ways to arrange the material, in the sense that first of all, considering every material, not just metals, we have a number of ways in which we can produce objects, produce semi-finished. Before that, we have semi-finished structures, which might be a bar, which might be a sheet, a tube, etc. From this, we can produce objects, so finished structures. We can see from this slide that there is a large number of procedures. This is general, so it doesn't refer only to metals, it refers to all materials. We can draw some general observations about this situation. First of all, plastic deformation can be a problem in terms of the fact that it may lead eventually the material to failure. On the other side, having plastic deformation means that your metal can be worked. If it can be worked, you can get to the semi-finished. It can be worked in different shapes, of course, and also the forces which produce a plastic deformation and which allow working may be different. You may have tension, you may have compression, you may have torsion. For example, you extrude and then you pull. Or in other cases, there is also the pultrusion, which is not an extrusion, but this is not exactly for metal. This is, for example, for plastics and composites. You tend to push and to get a bar, for example, a cylindrical bar. You can see that we have a number of possibilities. Some refers to metals, some refer to plastics, and we are going to discuss them later on in the next lectures. Injection, compression, vacuum, rotational molding. So you have a mold. In case of plastic, the mold is permanent. When I say permanent, I mean that it's not a single-use one. We use the mold for plastics many times to produce a large number of objects, which has a consequence that mold is, say, marginal into metals. We assume there is a mold, like it is the case in concrete. There is a kind of mold where you pour down concrete, but well, it's something which is not very expensive, and also doesn't really matter the precision of that mold. In the case of plastic, the precision needs to be absolute because mold costs many, many times more, in some cases, millions of times more than the piece we are going to produce. So in other cases, like for cast iron, like for concrete, I was saying, for some types of ceramics like clay-based materials, we have molds which just last once. So lost molds, we are going to lose them once we have completed the casting. And some fabrication techniques lost molds are very old, like the typical lost wax system. Other examples are much newer. For example, we can add material, like the 3D printing, we add material, and we complete the piece by gradually adding that material. In other cases, we subtract material. This is much more classical, like in sculpture, in woodworking, wood carving, and so on. Working with wood, we can subtract, remove material. Finally, there is another possibility. I don't pretend to be exhaustive, but I think it covers 99% of way of producing materials. From materials producing then objects and structures. Then there is the typical procedure which is used, for example, in shipbuilding, which is bonding different layers, adding and bonding and curing, therefore, different layers. Curing means that we leave them drying and bonding and be complete. Curing, it's a term which is applied also in concrete. You pour down concrete down the mold, and then you leave it for some time, dry in open air. This is called curing, and we have curing also in the composites. And curing means that you leave the composite to be bonded together. In particular, polymer matrix composites. When I am referring to composites, in most cases I refer to polymer matrix composites. Then, of course, there is ceramic matrix composites, like, for example, concrete. And there are also metal matrix composites, which cover a niche, which is quite interesting as well. And in the case that metals wear particular characteristics against wear, for example, and therefore you need to feed into metal some ceramic particles, like a typical metal matrix composites with aluminum matrix and alumina particles. I refer as matrix. Matrix, as you may know, it's the bulk of the material, whilst the filler of the reinforcement is the material which is added to complete. And coming back to metals, trying to concentrate to metals, we try to make a point on plastic deformation. Plastic deformation can be divided into two big categories. One big, really big category is the hot working. Hot working means that we are more than 60% of the melting temperature. Then we have cold working at the opposite, on the opposite side, and cold working means that we are below 30% of the melting temperature, both expressed in degrees Kelvin. Oh, and what we can say is that some of the differences are obvious between hot working and cold working. I mean that hot working doesn't allow strain hardening. It doesn't become harder because of strain. What we have seen, for example, in the example with nails last time, is that we harden. We have a strain, for example, nails are compressed by the hammer, by the action of the hammer. They are hardened. Hot working doesn't allow that because it's close to the melting temperature. And so in reality, the movement of the dislocation is too complex to create a real hardening. It tends to be quite soft material in hot working. In cold working, well, it exists strain hardening, of course. Nail are a good example because nail are heated up a bit by effect of the action, not much, a few degrees. And in fact, it's a kind of cold work. Of course, most operations of cold working are much, I would say, in terms of temperature. And some are very popular, are the ones which are most, some of the operations which are quite important in metals. For example, coining, coins, and, or drawing and punching, which involve some deformation, but not a great modification of the large modification of the structure of the material. So we are not changing hugely the geometry. In coining, you basically you have a punch, kind of punch that prints some image on the coin, and once you have cut the blank, I mean as blank, the semi-finished can be a round structure which has no image on it. So hot working instead involves a huge modification. We may transform, for example, a bar, an ingot, to a roll, ingot into a roll. That's substantial. Change completely shape. Pass from a kind of tetragonal, sort of tetragonal shape, you pass to a real flat sheet. You have forging, which is very used also in whenever metals have an ornamental sense. So in architecture, it's used a lot. Forging. Extrusion is very diffuse. And rolling, you may have hot or cold roll. And basically, you create some flat sheets, which you can then draw in other structures, and draw them in other. Because one of the important things is that we are not obliged, of course, to do just one of these processes. We may combine a number of processes. This is the most usual occurrence in the case of metals, that you combine a number of, and then you get to the final option. Of course, there is also a kind of warm working, which is in between the two, and this means that there is some strain hardening, but it's not substantial. But in general, we tend to move at the two extremes. Having discussed these first few things, it's important to come back to the point I was making a few minutes ago about the fact that we can combine a number of processes, even in a very simple object, say an aluminum can, kind of Coca-Cola can or whatever, which is a very simple object, and it's a few cents object. We start from ingot, then we we have these two semi-finished. We start from the first semi-finished from an ingot, then we transform by rolling, by cold rolling in aluminum in a rolled sheet. Then we cut a blank, then we draw to a certain height. Then we reduce further the thickness to a further drawing. We don't do that in one go, because we will destroy, by drawing it from the sheet, we destroy it from the blank, we will destroy it. Please remember also that it should be obvious that it's better to be precise. Of course, no stage in here is useless. Every stage is necessary to produce that object. Then you trim the irregular edges, and this is one source of waste. The other source of waste is shown to the right, is that cutting the blank from the sheet. Of course, you may consider when you cut the paper sheet and you want to make rounds or to make circles, you lose geometrically some part of the paper sheet. With aluminum, it's worse because it's much more expensive than paper, and so they found out that cutting along the diagonal, along an angle, you are able to lose only 12% of the material, which is enough already. And in fact, in a few cases now, since they go to recycling, this has been already been questioned, but probably geometrically you cannot go lower than 12%. It's important in other cases to choose the alloy in order to reduce the cost. I'll go into more details about aluminum alloys and about the types of aluminum alloys that exist that are large number. But as I was saying, to complete the can, we need to apply the and to close it. Of course, you print it with in order to locate the possible plastic sheet which envelopes it, and then you place the lid and you close it with seal. Okay, and trying to be scientific about the thermal treatments of metals, we have thermal treatments of metal which, as I was saying last time, they change the phases of the materials. We have tried to move back to steel because steel is always an example. Although we will give more details also about copper and aluminum, which are the three most used metals. The history of metallurgy, apart from bronze and iron, involved bronze, which is a copper alloy with tin. There were also some, in particular, a few metals which have a low melting temperature, which has been of considerable use during the centuries, which have been tin, which has the lowest melting temperatures of all the structural metals. Then we have zinc and we have lead, which have had a considerable history, and they are still used for some particular applications. For example, well, you may consider, for example, that in English, the person who's doing metalworking for hydraulic purposes. It's called the Plambo. French is called the Pommier, which means that they were using lead. They were using lead a lot into, for example, hydraulic purpose. Tin was used a lot also for welding, and zinc for alloying or covering, and so on. And so basically, we stick to this number of metals. Then there are other metals which are also used, like and other are used mainly to alloys, like chromium. This parenthesis, it's important to remember that thermal treatments can be influenced by a number of factors. Basically, they are influenced, of course, by the temperature. This is obvious, because you may expect that if the temperature is different, the results. But they are also influenced by the time at which they are maintained at that temperature. And here you have the large difference between metals and plastics, because metals are conductors. And so you may keep metal for a considerable time at that temperature, and it will reasonably stay at the same temperature the whole of your semi-finished, for example, of your metal bath is melted, molten. You can consider that instead for plastics, the requirement is always that it stays as little as possible at high temperature. And then the problem with plastics is that they cool down in an uneven, non-uniform way. But we will come back later on to that when we will discuss about polymers and so on. And then the method, because I can cool down by simply leaving them down my place, like it is the case for concrete. Well, I take off the mold from concrete and then here until it dries. So with metal, we have different options which influence, of course, the time and also the presence of internal stresses. I can do that in cold water, so it's going to be fast. And in oil, in air, of course, or I can even send an air stream. I would say that temperature and time are two main factors. Of course, time has a correlation with method, because strictly speaking, I have first to decide the method to obtain the time I want to have, because the time becomes very critical to obtain one phase or another. This is important. You may have realized from the diagram, the state diagram of iron and carbon, that we have different phases. For example, austenite, ferrite, cementite, a different content of carbon, and then a different temperature. The time wasn't involved in that graph. We need a further graph where time is involved, and we show this later on. But it's important to have the idea of the different names which are given to the different operations. Annealing is heating the metal, which allow reactivating the motion of the lattice. So you heat the metal. Annealing is the first thing you can do. Well, annealing means heating with no particular control of the temperature. I just and I'll have a relief of internal stresses, etc. I increase ductility. In some cases, I may also improve hardness. It depends on the temperature, really. Depends on the temperature and it depends on the alloy. But annealing, it's a kind of not very controlled temperature operation. Quenching means that I cool down in different ways. When you say quenching, I am cooling down after that operation of heating. Then there is tempering. Tempering means another thing. Means always a heating, but it means that I need to control the temperature because I would like to get to a particular phase instead of another. Because I want to improve the toughness. Remember that the toughness is the resistance to a defect, to the presence of the defect. The fact that the defect doesn't expand, doesn't grow, especially doesn't get to the critical, having that critical energy that allows the defect to proceed to fracture no nuances. And in tempering, it's also important to ease the dispersion of alloying elements, the other elements. Because you were thinking of iron and carbon, but there are other factors, other metals that enter the picture. The most typical ones are nickel and chromium, but there are many others which enter in the simple case of iron. An example is manganese and many others. Therefore, if I want to, a number of problems, I would say, in metals are given by the fact that the alloy does not diffuse in an even way. Doesn't diffuse uniformly in the one thing which is obvious, we started to thinking of that beforehand, is the fact that element, since it has obviously a different atomic number from iron, behaves in a different way and creates defects. Behaves in a different way because it has also a different melting temperature. If you want to melt a simple alloy, an alloy with between iron and carbon, if you have just iron, you are above 1,500 degrees. Then if you include carbon, then the temperature is starting to change, as you see in if the second, if you add a second alloying element, which might be even a very low temperature. If you add zinc, for example, you may get in trouble because your melting temperature goes really down. Because of course, melting temperature depends on the relative amount of every alloying element. And then it behaves like a defect. And in addition to that, the influence of temperature might be very different depending the alloying elements you have. Okay, we proceed with a very simple example of a diffuse treatment which is applied to steel, which is hardening and tempering. Hardening means that you go above A3 temperature. If you come back to the graph, to the iron carbon phase diagram, you can see two particular temperature, which are 912 degrees and 740. By hardening, you overcome both of these temperature, and as a matter of fact, you make your steel quite brittle. Of course, you quench it and you make it quite brittle. I'll give more details about that later on, because in reality, this is a very typical operation. You have the hardened and tempered, steel. So usually the situation is the situation to the right, normally at both of them. Unless you want to have a very hard steel, but also very uncontrollable steel, you need to have H plus T. H plus T, and tempering, it's below, you heat up and then you quench. Normally, you keep it for more time, and you, in most cases, you try also to be slower, heating up. In quenching, I show that straight line because in reality you have temperature and time. You have temperature on the y-axis and time on the x-axis, but in reality it's difficult to tell. It depends on your needs. But you can also delay a bit. Quenching, you can have also a quenching in air, which in large steel works is quite typical with quenching. For example, or even hold the roll that sheets into air. But in other cases, you need to be faster. But apart from that, this operation, whilst hardening, leads to a brittle and not very controllable steel, but very hard. Tempering relieves the internal stresses and makes it more usable, more workable as well for further operation, because you are not at the end of the story. Even if you have the semi-finish, then you need to work it out, cut it, and so on. And of course, it's very hard. You can understand that the cutting might be the operation. This is an example. For example, this is a piston rod, which is obtaining forging. For example, here you have hardened and tempered, and then you have forging, which means that you heat it again, probably not at very high temperature, but you need to work it again. And hardness, to complete what we were saying on hardness. Well, this is not complete because you will have then the hardness testing on plastics and on ceramics. We have different ways of measuring it. Basically, hardness is a technological test. It's not a mechanical, because you have empirical scales. I've shown you before the Brunel hardness, and the image referred to Vickers hardness. So Brunel is with a steel ball, Vickers it's with a diamond shaped tip. In reality, what you get is an indentation, a dent, which has, in the case of Brunel, it's not circle, it's sort of a circle. It's more, here it's represented like it was a circle. This is the ideal one. In reality, it's a kind of, even not an ellipse. It's a kind of in between a circle and an ellipse. It might be also not very regular. And Vickers should, well, you would expect it's a kind of rhomboid, but it's here again, it might be irregular. These two questions are the irregularity of the indentation, are an example of the practical consequences of still not being really ideal. Even if it is close to ideal, when you go in small dimensions like this, it's a test which is done in the order of tens of millimeters or so. You see that they are not really regular. The resistance, the strength is not and it's not constant across the section, and you may see the consequence of this is that there are variations. There are variations in between the dimensions of the indentation, and as a consequence, it's difficult to measure. That's why it was developed also. The Brinell and Bikers are useful because they are very quick to perform as tests. Not very quick to take the measurement, because then you, in fact, then you need to measure. In fact, now there is a micrometers because you do that but under the lens of a microscope, and therefore the measurement of the diagonals are now made almost automatically by, well, semi-automatically, in the sense that take some measurement, but we need to verify if the measurements correspond to what we really see, because it takes in question of pixels, but we need to decide if we are happy with that. But anyway, it increases the reliability of the measurement, and it reduces the difficulty. Then another type of measurement that was introduced, which is the Rockwell one. Rockwell measurement has got a number of different possible scales. The one which is used on hardened steel is the Rockwell C. And the difference of the Rockwell measurement between, with respect to Brinell and Bikers, is that you don't have a measurement on the indentation. Your measurement is done on the length that it penetrates, on the length across it, which it penetrates. What is done in practice that you apply an initial force, then you indent, and therefore by applying another force, and then you see which is the real penetration with respect to the zero line, which has been decided, and the whole length, the whole thickness, which needs to be known. In fact, you have this kind of constant, which is given to that thickness, and then you have the measurement of the penetration. Practice, you obtain a direct length, which is instead of measuring that indentation, which might be cumbersome in some cases. It's a very fast test, the metal hardness, and also for plastics and so on. It's very interesting doing hardness. Why make clear the fact that hardness seems quite imprecise, and in fact, in some cases, it might be imprecise. What is done on hard, what is the difference between a tensile test, say, or a compression test, and hardness, is that tensile and compression tests are made on samples. This is made on the real piece. You can have hardness measurement on pieces which are possibly, you may have a semi-finished, and you have seen with aluminum can, there is a part which we will discard, and we know which part we are going to discard, and so we may take measurements of hardness, for example, on the part of metal, steel, sheet, steel sheet which we discard. To know which is the quality. So these are quality measurements as opposed to the ones which like tensile tests, which allow to establish the specification of the material. The specification of the material is intended like these sheets of paper full of the different properties, physical, chemical, and so on, which are given to you when, for example, you buy a set of, say, metal sheets. And therefore, we need metal tensile tests or compressive testing establish some properties of the material. Hardness is more, give us more the control over the technological properties. So we need, if the process we are applying, for example, treatment, the heat treatment, we'll extend that question also on plastic, where the control, the quality control is even more complicated than with the metal. Bearing in mind that we tend to concentrate on material science as opposed to material technology, because material technology probably need many more hours than we have. But material science is a kind of preparation to material technology. We want to know better material in order to know what we can produce technologically. And I was talking about heat treatment. Heat treatment means that we have temperature and we try to transform one phase into another by using a definite time. And for example, in phase diagram, in iron carbon phase diagram, we weren't considering an actor which is in reality important, phase which is in reality important, which is martensite. Martensite doesn't occur in iron carbon diagram in general terms. It occurs only when the diffusion of carbon atoms has an effect of heat treatment on thermal modification occurs at a fast rate. So it's an effect of transformations. And as the consequence, we have this temperature time transformation diagram, which says to us in which interval martensite does exist. In fact, we have 2 points which are martensite start and martensite finish. And between these 2 points, there is this curve which represents 0% of martensite, so the martensite start, and 100% of martensite. So there is this interval, 100% in terms that we have completed the transformation to martensite. From austenite we transform to martensite, and in practical terms, martensite doesn't occur above around 700 degrees, because beyond that we have an austenite which is stable. The austenite, you remember, face-centered cubic crystals. or lattice. Martensite is tetragonal, and it needs fast time because if you take hours, you can see that here you in most cases the temperature would be very low to get martensite and low temperature. There is a right interval of temperature and in which you have martensite because austenite becomes unstable and then you have if you are particularly fast it becomes unstable because you don't give it sufficient time in uh, cooling down in allowing carbon to diffuse. And since you don't give it sufficient time, what happens is that it does not diffuse regularly, but instead the material is deformed to take the form of the crystal lattice in the diagonal. Um, we have other different actors. If you wait, if you are at low temperature, you wait time, a long time, you have martensite plus bainite. Bainite may take a form which is more compact, more amalgamated with martensite. Um, and the advantage, the difference between martensite and bainite is that bainite doesn't need any treatment. It gives you sufficient hardness, but it's adapted for large pieces. If you want to have a small piece which is hard, if you want to make a knife, you would need martensite. Then a knife is brittle, but it's not a problem because you don't often drop a knife. But it cuts. With bainite, you would not have the possibility to cut, but you may create large pieces which have a sufficient hardness. Of course, if you go up to perlite, you go into a region of kind of ceramic. In fact, in some cases, it might be quite brittle. You don't really make large pieces with perlite. More details can be given about that. In some cases, bainite is quite interesting. For example, the upper bainite, you find this kind of feathery appearance, which is also of interest. Perlite is more typical of created into lamelle instead of having a martensite which has this typical aspect and you find this only this the presence of only martensite. You find it inside there. So in a few minutes you have the temperature of transformation in a few minutes quickly you go up at this temperature and then you burn. So it's a question of transforming it in one phase into another, which is very connected hardness again. You want to get some hardness, which is a technological property. Here we find Vickers ceramic hardness, pH hardness. You may think that martensite it's hard, less hard than that region. You may consider that that's harder, but in some cases for larger structure, as I was saying, the maximum is very large structure. Because of the slow diffusion of the fast diffusion of carbon structure makes material very. Steel, from steel we pass to copper. For copper has got a long history, of course. With copper, you started from copper alloys, so bronze and brass. So brass is the alloy with copper mix. And although in commercial terms they are often they are all used and intended as bronze, but in reality, if you stick to the right terms, not the commercial one, the alloy with tin, the alloy with zinc, brass. You can anneal copper, so you can heat it up at some temperature with no temperature. And what you find out is that you can get a considerable, you reduce your strength, your stress, your ultimate strength, and you have a large tensile strain. You have a large tensile strain which can be used for annealed copper, which can be used for some mechanical operation like cold drawing, for example, for an application of iron. And there are some other applications, so hydraulics and so on, and also in architecture and buildings. But in most cases, since it is the best material for as a conductor, as the combination between conductivity and cost, because gold is more conductive than copper, but it costs much more. So in fact, it is used, for example, in small circuitry like the one for cell phones and so on. But copper is used. Okay, so in annealing copper, you get a longer deformation, plastic deformation, so it's more, can be more in other cases, you may consider that you can treat copper, you get the cold roll copper. Here, the purpose of the graph to the right is that to understand, well, I want to make a copper sheet, because in some cases you need electrical transformers and so on, sheets of copper. And I would like to understand how much hardness I use if I want to hold the roll copper or roll copper. The question is, the rationale of this graph is that at 300 degrees, that don't lose much hardness. This is Brinell hardness, so it's doable. I can do that. It's feasible. Then you can go down, down a lot, passing at 400 degrees. Maybe I may need 400 degrees, and it's already sustainable. 500 degrees, if I heat up at 500 degrees because it's needed by the heat treatment to make my piece, then I lose hardness, and possibly I may have the wire, but then it's not hard. Awkward. You know that electrical wires and larger structure need to be coated to make the structure. Okay, copper needs to be very pure to work in electrical cables, electrical uses, and fact not below 99.9, preferably higher than that. And you may have a small amount of oxygen in terms of parts per million. And oxygen is usually used in fabrication of copper. That's why it stays inside, because it remains a bit, because it dissolves impurities of copper. That's how it's done to have so pure oxygen. And if there is more than needed, it's then eliminated by phosphorus. Some oxides are insoluble in, therefore remain. But if the amount is between 175 and 45 parts per million, it's okay for electrical application. Also, copper has got state diagrams. We are not going to go into much detail about this, but what I can say, what is important to see, you can see a large area. This is to the left, you have bronze, to the right, you have brass. So you have tin, and then you have zinc up to the 60%, because then you don't have really much interest. Zinc alone, it's quite rare that you find zinc alone. You find zinc mainly in coverage, plating of steel or other metals, because it doesn't allow oxidation. And you find it into brass, into with copper. Also in alloys with aluminium, steel in some cases, some small quantity. Okay, and so you can see in both graphs that we have a large alpha area, especially in brass, and it's where the materials are normally used, because then you have more brittle areas in the case of brass. In the case of bronze, we have alpha bronzes and alpha plus delta bronzes, which are good as well. And so in practical terms, all these graphs say to you at which kind of temperature, at which level of temperature I can get in order not to get transformation, because here you get to, when you, in the case of bronze, when you get to the epsilon phases and so on, you get to phases which are much more ductile in a sense, but on another sense, they are not much workable, and they tend to also to expand considerably over time, to degenerate into voids and so on, like it is the case of tin. Tin has been used a lot, because you see it has 232 degrees of melting temperature, so it was really an opportunity for men in ancient times to use this kind of material, because it was an easy material to shape. On the other side, we can see that this means large plastic deformation, large yes, workability, but also unreliability of the network working. So limited precision and so on. So in industrial terms, it went out of use for most users. It still used quite considerably for welding. We were giving just a hint of corrosion. Corrosion is a big problem in metals. And in the not many minutes I want to talk from you, I just give you an idea of what corrosion is. We will concentrate more on corrosion, because there are a number of studies on corrosion. It's a central problem. metals, not only into metals, because also plastic have got their particular type of degradation which can be correlated to corrosion, and also the same can be said about concrete. Concrete has got a large problem of corrosion due to the steel bar, the iron bar, the steel bar which are introduced inside, and as the tensile strengths vary. So in practice, reinforced concrete has got a number of discussed later. But it's important first to understand what corrosion is. Corrosion means it's different from oxidation, because you may have an oxide, but the oxide is stable and stuck to the metal, and therefore it's not a problem. Aluminium, anodized aluminium, has got an oxide which is stuck permanently on the metal and doesn't allow corrosion to progress. What happens in reality with corrosion is that you have a detachment. You lose some material, or you can have a swelling of the material. Because, for example, water vapor also can penetrate the material. You have, or even hydrogen may penetrate. Work in some situation, you may have a kind of hydrogen rating. You work with acids, for example. In acids, you have hydrogen. Then hydrogen can penetrate the material as a result. Or you can have other situations like again you can have a uniform corrosion like in A, or you can have a kind of pitting deformation pits, which are given by some acid conditions which are very localized or can be less localized. Or you can have a stress corrosion. You have a corrosion given by the fact that the material is subjected to a stress, for example, from frequent movements. We are going to discuss about fatigue later on, which is also. And you may have, as a matter of time, you may have some cracks. In other cases, in alloys, like in brass, you may have the fact that that's why you don't do much with more than 30% zinc, because zinc and copper have a quite different properties, and you may the fact is that zinc might come to the surface, because they have also may gradually come to the surface and separate, but they have also a different density, and zinc may come to the surface and in the end may be removed. Because zinc is very protective of what is below. If it is pure zinc, but if zinc is isolated into a bulk of copper, to make it simple, it tends to come out and to expose further material. In case of copper, to complete a bit the question about and the conductivity, you can see that tin might be interesting. On the other side, you might have to consider that tin is not very interesting as such, but it might be interesting for covering some copper cables. Because what happens in practice, that copper doesn't suffer corrosion. Copper doesn't suffer corrosion unless there is water. If there is water, and even worse, salt water, in fact, at sea, in some cases, other materials are also used for creating cables. There are alloys which are we may discuss it later on if we have time, but problem with the relation between copper and water, especially salt water and acid water, it's difficult. In some cases, especially if you want to keep it cheap, because tin is cheap after all, you may consider covering the cables with tin and for corrosion. Don't think that if you put two metals together, it's always going to work well for with corrosion, because in some cases you may have galvanic corrosion. So they might form also a kind of dipole and then sort it out. But in this case, it works. The question with impurity is that in some cases in some cases you find out that also the resistivity and therefore the conductivity is the inverse property than the resistivity. You may find out that the conductivity is reduced by the presence of impurities. So there is not just oxygen. Oxygen in general terms is acceptable, but there are the oxides that oxygen is not able to scavenge from the cable. So in the end, there are this number of possible impurities with different activity, with different negativity respect your material, the conductivity of copper. I don't go into details. It's important to know that the question of input on its conductivity, on its electrical thing, which has as well a relation between those. It's important. The Joule effect and so on. In that case, there is also a question of dispersion. Change also thermal properties. It's important to know the effect of impurities even in as a question of so PPA. We started talking about Odyssey and so on. It's important, it's an important sector in science, which I can give also some small archaeometallurgy. Archaeometallurgy means that we'd like to understand, as we started from, how in ancient times they were able to produce the artifacts, bronze, iron. Talking about bronze, there are a number of studies on corrosion of bronze in archaeometallurgy. Here we find out a bronze artifact, cross-section of bronze artifact. There are some areas of corrosion, and with the X-ray diffraction, which is normally coupled SEM to the scanning electron microscope, you are able to see the signals which are connected to different areas. So which kind of elements you find. In some cases, since it is bronze, if you have copper and you have tin, SN, copper and tin, that's fine. All the rest is doubtful. You find, but some are more doubtful than others, are indicators of corrosion. Silicon is not a problem because silicon, in ancient times, it was difficult to get rid of silicon dioxide of silica. Usually get this kind of production in mixed up, you extracted, you smelted your rock, and there was possibly some silica and some aluminum. So silicon and aluminum are not strange to find, and also of course some iron. normal that there are also some iron oxides, the rock from which you extract the bronze, just the bronze, the copper alloy just by it. So by extracted from the rock until the metal part melts and the rock stays there because it's higher temperature of melting temperature. But what is worrying really, and you find it in 3 out of 4 regions, it's chlorine, because in reality this indicates that has been some reaction that has brought to some corrosion. So you have copper chloride, which grow as corrosion products on the surface, and they are gradually detached. And this gives you an idea that these techniques can be used to see to qualify the presence of corrosion to the structure, and also to correlate, why not, with the history of the artifact, depending on what it has been exposed. For example, presence of seawater or environmental condition. This is just said to give you a hint of what general sensitivities. Because, as I was saying from the beginning, our idea is to concentrate on the teams, possible research teams, and try to understand if and go deeper into some of this to understand what's going on. The general science context. Corrosion there are some other types of corrosion which are very typical. You may have realized that metals like steel have got grains which are the places between which the alloys precipitate. The second element, possibly, if you which might be carbon, or you may have more elements like chromium, for example. In ferritic steels, you have chromium. I am going to talk it later on next time, but you may consider that basically you have ferritic steel with chromium and austenitic steel with, again, chromium, but nickel as well, which have different properties. I would make a bar for a construction into ferritic steel. I would instead I would make a smaller a structure like the ones used in the structures, kitchen objects, smaller kitchen objects, like a pan, for example. I would make it austenitic steel. And for example, here we have aluminum instead, and zinc has precipitated between the different grains, and it has created the cracks, as well, which led into the failure of the aircraft component. And in that other case, this is an archaeological artifact, and you have a ring in practical terms, and you have, look at the microscope, you have this fragment. You can see an intergranular corrosion. Again, you have tin in the case of the bronze, which has gone disalloyed into intergranular. Okay, we are almost at the end. We will complete the question about oxidation and then passivation. Oxidation, you may know that you have electrodes and you have one pole which is the anode, the other pole which is the cathode, and at the anode it's where oxidation occurs. There is a good oxidation and a bad oxidation in terms of corrosion. Because if the oxide is stuck to the surface, here you can find titanium, for example. Titanium and aluminum have got this particular condition, which is good. And you can decide that you want to have a further oxidation, so to increase the thickness of the oxide, and then you have anodized aluminum or anodized titanium. Anodized means that you see that there was this natural characteristic of forming another oxide, this alloy. Then you want to make further oxidation occur, so the thickness of the oxide layer is higher. This is used, for example, if you make windows extruded parts. It's very good to have an oxidation. In many normal objects, also used in architectures and in buildings, you find this anodization. There is also a steel product for completeness that has this kind of sort of oxide, which is quite adherent, but not in presence of water. And it is the so-called core 10 steel, which is very used. This is the obelisk in Terni, which is made in Corten, a triangular structure in Corten steel. And Corten steel, it's a low alloy with a limited amount of carbon and very little chromium, but sufficient to, together with other alloying elements, to create this rust-like oxide. So it looks rusty from the beginning, but it stays there unless there are some water infiltrations which might create a foam. This is a patent which was started in the 30s in the US, and it has been extended use over especially architecture and because it is stable. The rust-like oxide is stable. It's different from anodization, but it is the same as for color, because anodization has the big advantage, as you can see from these maps, that you can color it. It's so thick, and so whilst 200 microns can be the anodization thickness, but so stable that it can absorb any kind of color. So it gives you opportunities which most cases with steel are not very easy to achieve. And also it's much more stable. That's why also anodized aluminum expressive. Corten instead creates that rust-like oxide which stays there, and it's a compound of oxides present there, particularly the ones from chromium. Okay, so we'll see you again on Friday. Please try to make your mind about which kind of subject are you most interested in. I'll repeat this a number of times. We have, of course, still a number of and I try to intercalate one with the other as much as possible and give an idea of the whole core of studies which are performed on science, at least most important subject. You see, it's very multidisciplinary, and it's also very connected with normal life, real life situations, like phenomenon corrosion, for example, which is very for in life, extend this subject. So, okay, have a nice following this week, and see you on Friday at